Hi everyone, my name is Alex Krolewski and I'm a postdoc at the University of Waterloo and the Perimeter Institute. And today I'd like to tell you about some really exciting new results we have for cosmological constraints from CMB lensing cross-correlations. I wanted to start off by thanking my co-authors, Simone Ferraro, Martin White, and Eddie Schlafly, who are really critical to the completion of this work. And in this talk, I'm going to be drawing work from the following two published papers, and I've included the archive links below. And so I just wanted to start off with some motivation, and our motivation in particular for this work was the recent tension in the low redshift amplitude of structure, seen most particularly from recent stage 3 lensing surveys. And so the idea here is that lensing surveys constrain sigma 8 and omega matter, and actually they have a degeneracy between the two, and so often the constraint is expressed in terms of S8, which is a combination of the two. And a number of lensing surveys, as well as a few other surveys, have found S8 to be a little bit lower than the value from Planck. And so that's illustrated in these figures here, where I'm showing Planck constraints and then kids and DES and a kids plus DES reanalysis. And you can see that all those contours are a little bit lower than Planck. There's about a 2 to 3 sigma tension. And it's really interesting. We want to know, is this indicative of some new physics beyond the ΛCDM model, or is it coming from systematics in the measurement? So therefore, we wanted to test the lensing tension with a similar measurement with different systematics. And to do that, we used weak lensing of the CMB. Rather than using shearing of galaxy shapes, we're actually looking for lensing from distortions in the cosmic microwave background. And so the cool thing here is that the lens is almost all of the matter in the universe, so we can probe to significantly higher redshifts than with cosmic shear surveys. So on the bottom, I'm showing the CMB lensing kernel, which peaks at about redshift 2. Now, how do we extract the signal of lensing from the CMB? Lensing has a tiny impact on the observed CMB, but it's a very distinctive one because it leads to non-Gaussian correlations. So that's shown on the bottom right. So first I have the unlensed CMB temperature, and then the middle panel shows the change in CMB temperature from lensing. And you can see that this is a very small impact, but it really looks very different from the primary CMB. And so we can exploit this to write down a statistical estimator for the amount of lensing. And then on the right is showing the reconstructed mass along the line of sight. And so this is great. This is great that we can reconstruct all the mass out to the CMB. The disadvantage is that, unlike in the case of cosmic shear, we can't look at source galaxies at a different redshift. We just have one source plane. That's it. So if you want tomographic information, you need to do something else. And in particular, you can get tomographic information by cross-correlating CMB lensing with galaxy samples at different redshifts. And each cross-correlation is then going to actually probe the matter at the redshift of the galaxies rather than all of the matter out to the CMB. The other advantage of using cross-correlations is that we can actually get more information from the cross-correlations than from the autocorrelations alone. Now, the complication when we introduce galaxies into our CMB lensing measurement is that galaxies are biased tracers of structure formation. Their clustering is enhanced relative to matter. And so, here I'm showing the classic peak background split picture, galaxies forming at the peaks in the matter density, which causes them to be more clustered than the matter, and therefore have a higher amplitude of the power spectrum. And so what this means is that we need another observable besides the galaxy-CMB lensing cross-correlation, CL kappa G. And we do that by also adding the galaxy autocorrelation, where you now have 2 powers of galaxy bias instead of 1. And so that means that you can just combine together the auto and the cross and pull out sigma 8, or more generally, the amplitude of the matter power spectrum. Now, it turns out that we can define galaxy samples with a very high number density and low shot noise, and therefore we can measure the galaxy autocorrelation with quite small error bars. In contrast, the CMB lensing cross-correlation is limited by reconstruction noise in the CMB lensing maps, and so therefore it generally has higher error bars in the galaxy autocorrelation. What this means is that the signal to noise of sigma 8 is going to be equal to the signal to noise of the lensing galaxy cross correlation. So to get better cosmological constraints, this really boils down to how well can we measure the cross correlation with CMB lensing. So how do we build the highest possible signal to noise CMB lensing galaxy cross correlation? And it turns out that the best way to do this is actually by using a very small infrared satellite called WISE. And WISE has a few advantages that make it uniquely well suited to CMB lensing cross correlations. The first is that it's an all-sky mission. And this means that we can really take advantage of the fact that this synergizes well with our best CMB lensing maps, which are coming from the all-sky Planck mission. And this is a big advantage over optical surveys, which typically cover only one of the other hemispheres. So this is basically a root 2 gain by using WISE. The second big advantage of WISE is that as an infrared survey, it is particularly sensitive to higher redshift galaxies. And this is just because you're redshifting the galaxy to a point in its spectrum where it's actually gotten brighter. And therefore, galaxies at redshift 1 are actually easier to pick out in these infrared 3.4 and 4.6 micron bands than they are in the optical. And so I'm showing a redshift 1 LRG on the bottom, in optical on the left, and in WISE on the right. And even though WISE is a much smaller telescope than Sloan, and the image quality you can see is poorer, it's a lot easier to pick out this galaxy. And this is particularly critical for CMB lensing cross correlations, where we really want as many galaxies as possible towards that peak in the lensing kernel at redshift 2. And so basically the combination of these factors means that WISE is actually the best instrument that we have for doing CMB lensing cross correlations to high significance. In our work, we're actually using the unWISE catalog, which has an additional 5 years beyond the original WISE mission. And it's publicly available at the URL here. And there's been a ton of work led by Aaron Meisner and Eddie Schlafly mainly on producing this catalog and reducing the WISE images. Great. So we have this huge all-sky catalog of galaxies. Really, we have a huge all-sky catalog of sources with fluxes in 2 infrared bands. So how do you select galaxies from just 2 infrared bands? It actually turns out you can do quite well. But of course, it's hard to differentiate stars and galaxies. You always have some stars creeping into your selection. And so first of all, we start by taking our sample and matching to a Gaia catalog of stars. And it turns out that Gaia is quite well matched to WISE. And once we do this, we basically eliminate stellar contamination. Our residual contamination is around 1%. So that's really great. And then second of all, it turns out that even with just the 2 WISE bands, we can form 3 broad redshift bins. And so here I'm showing the WISE color redshift plane. Redshifts are taken from very deep photometric redshifts in the cosmos field. And the cuts that we use in our samples are shown in black. So we can create 3 samples, blue, green, and red, in order of increasing redshift. Redshifts half, 1, and 1.5. And the table is showing the number densities that we get. And these are very, very high number densities for galaxy samples. And so here I'll just show you the maps that we've made. So here's the blue sample. You can see things look quite clean. And of course, take note of the fact that we have both hemispheres, since this is coming from an all-sky satellite survey. And here's the green sample at redshift 1, and then the red sample at redshift 1.5. And now, of course, the number density has dropped quite a bit, so this sample is not going to be as important for our cosmological constraints. On the CMB lensing side, we use the best publicly available maps from Planck. So they've detected CMB lensing at about 40 sigma, and this is the map that they use. Now, the next complication is that we need to know the redshift distribution of our galaxy sample. We only have 2 infrared bands, so photometric redshifts are just going to be totally impossible. We could try to take our sources and cross-match them to good photometric redshifts from optical or spectroscopic redshifts, but this is difficult. Deep enough redshifts are only available in very small areas of the sky, so there's a lot of shot noise, and a lot of cosmic variance. And so instead, we go a slightly different route, and we use clustering redshifts. And clustering redshifts, the idea here is that if you take an unknown photometric sample and you cross-correlate it with a spectroscopic sample in a very narrow redshift bin, the amplitude of that cross-correlation is proportional to the number of photometric galaxies in that narrow bin. So you just repeat this measurement with a number of different spectroscopic slices covering the whole redshift range of your sample, and then you can build up the redshift distribution. Now, one complication of this measurement is that, of course, since you're doing a cross-correlation, you're not only going to be sensitive to the redshift distributions, but also to the biases of the sample. The bias of the spectroscopic sample is easy to measure. We're using spectroscopic samples from SCSS. They've been very well characterized, very, very clean samples, and we can just go out and measure the spectroscopic bias ourselves. The photometric bias is harder. Basically, it's impossible to disentangle the photometric bias evolution from the redshift distribution. So this is a bit of a problem if you actually need just dNdz. But of course, in our measurements, wherever we have a dNdz, we also always have a galaxy bias, since the dNdz is only coming in on the galaxy side of things. And so in fact, the fact that we are also measuring the bias evolution is actually a feature for us. It's actually great. It reduces our modeling because we now don't have to model the bias evolution with a separate free parameter. And so here on the left, I'm showing the cross-correlation measurement. And just as validation, I'm comparing our measurement to a different cross-correlation redshift measurement produced by Yiquan Cheng's publicly available tomographer tool. And the agreement here is really quite good. And so that's very encouraging. And so here I'm showing the cross-correlation measurements again. And here I want to emphasize that these clustering measurements are noisy. We're limited by the number of spectroscopic objects that we have. And so basically at each redshift, we have a point and we have some error bars. Those are the red point and error bars. And we can interpolate through those points to get a best fit redshift distribution given in blue. But of course, there's also uncertainty in that redshift distribution. And so I've also shown a number of different samples from the redshift distribution in the light gray lines. And later in our cosmological analysis, I'll tell you how we propagate this uncertainty. And I also want to point out that you see a few high redshift bumps, but we think those are likely noise. They're not seen in the cross-matched Cosmos photometric redshifts. To model our galaxy cross-correlation and autocorrelation, we use a hybrid perturbation theory and empirical model. Mostly consists of linear bias times halo fit. And then we have some small correction terms that add nonlinear bias and We also have shot noise for the galaxy autocorrelation. Because we're using relatively large scales, the higher bias terms are quite small, and so in fact we fix both the amplitude of the higher bias, the shear bias, and nonlinear bias B2, and we also fix the cosmology in those templates. And on the bottom, I'm just showing the scales that we can model. So of course, since this is a photometric measurement with relatively broad bins, we are measuring angular power spectrum and not 3D power spectrum. And so our maximum angular scale corresponds to a range in physical scales. So what I've done is I'm showing all of the K modes that contribute to our L max for each sample. But you can see, generally we're going to about K of 0.2, 0.3, with some tail out to higher K that's coming from the very lowest redshift galaxies in our bins. And here, and so we also include a few other things. We have magnification bias with the 10% prior on the number density slope. And then, so at the end of the day, we have a 5-parameter model. There are 2 cosmological parameters that we're varying, omega matter and the amplitude. Linear bias, we have a slight freedom in this number density slope, and then we have the shot noise. And so here on the bottom, I'm just showing those different terms, autocorrelation on the top, cross-correlation on the bottom. So the linear bias term is dominating. Then we have a small contribution from the higher order terms, a small contribution from magnification bias, and then we also have shot noise. And then, of course, we're also marginalizing over our uncertainty in the redshift distribution. To validate this pipeline, we construct some mock tests. The goal here is just to have plausible mocks. It's not to calibrate our model, so we don't really take these models too seriously. But what we do is we start with an approximate n-body simulation in a very large box. We populate galaxies following a basic HOD, adjusting the parameters to match the bias evolution, observed redshift distribution and power spectra. And down on the right, I'm showing that match. And basically, we're matching the power spectrum for about 10%, so good enough for a plausibility test. And yeah, and so then what we do is we apply the same pipeline as on data as on the mocks. And here you can see that we can recover unbiased cosmology. So the contours are for each of the 3 samples. And the dotted lines are given the true cosmology. And so you can see that our constraints are centered well on the true cosmology, biases of less than ½ sigma. We also need to include uncertainties in the redshift distribution in the real data. And we do this by taking all of those different samples that I told you about, sampled redshift distributions, and just running chains with each of them. And then we average over those results. So the left panel is showing how this works. You have many different contours, and this is basically spreading you out in the S8 direction. So shown in contours on the right, going from the red to the blue, increasing your S8 error by about 20 to 50%, with the largest impact for the blue sample. And so, without further ado, here are our cosmological constraints. So I have the 3 different samples in blue, green, and red. And you can see that they are quite consistent with each other, so allowing us to combine the constraints. And they are also lying a little bit below the Planck results. So lensing tension, what do we have to say? Unfortunately, our results are quite similar to previous results. Unfortunately in that this is still a 2 to 3 sigma tension in this sort of murky area of what exactly is going on. Nice that we're quite consistent with kids and deaths. Now, one caveat is that if we free B2, our error bars would increase. Although I will point out that our fiducial analysis with fixed B2 is quite unbiased on mock, so I think it's a reasonable thing to do. But if we free B2, we can restore concordance with Planck at the price of a somewhat implausible B2 value. But we're currently have work in progress to better constrain B2 by extending the scales that we can model. And so that will tighten our constraints. And so here's a sort of summary plot, status of the S8 tension right now, our work on the top in red, and then a number of different low redshift results in black, and then CMB in blue. And you can see, generally lower S8 from these low redshift results, a little bit of scatter, a few outlying results at higher S8, but it's a pretty intriguing picture of low S8 coming from low redshift. And finally, I just wanted to leave you with the slide of our next steps. Our biggest area of improvement is better modeling, but we're also incorporating more data sets.